Welcome to Fundamentals of Artificial Intelligence. Today we look at heuristic functions. In the previous lecture, we had looked at uninformed search strategies. Uninformed search strategies do not use any problem domain information while looking for a solution in the problem space. Informed search, on the other hand, exploits problem domain information, which we refer to as heuristics. In this lecture, we will look at more closely what heuristics are, how heuristics could be formulated for a given problem, and we will list certain properties of heuristics before we move on to informed search strategies in the next lecture. At the end of this lecture, it is expected that we would be able to understand or define heuristics, would be able to formulate heuristic functions, look at how heuristics and AI search are intricately related. We will look at the design of heuristic functions through a method called problem relaxation. And then we will look at what are admissible heuristics. We will look at what do we mean by dominance between given heuristics. We then go on to define something called composite heuristics and look at consistent heuristics. Heuristics is a Greek word which would mean find or discover. It usually is the study of methods and rules of discovery and invention. Here, we use our knowledge of the problem to consider some, not all the successes of a given state. This means we will be able to prune the state space, gaining speed. But then the risk is perhaps we would also be missing the solution. Therefore, designing a heuristic and working with heuristics is of utmost importance. Heuristic functions are able to rank the children of a given node. And a heuristic function takes a state and returns a numeric value. It is somewhat like a composite assessment. We choose a child with the best score, and a heuristic function can help gain or lose a lot. But finding the right function is not always easy. Heuristics in AI search has a very specific meaning. It is a function that estimates how close a state is to a goal. In the next couple of slides, we'll look at what we mean by that. The heuristic function takes a state and it returns an estimate of its distance, its cost of the path from the goal. Here it would be appropriate to think of an example from real life. Like if you want to go from place A to place B within your city, Euclidean distance could be a good estimate of the distance between A and B. However, we need to note that the Euclidean distance may not give the correct distance between A and B. The actual distance would be different. What the Euclidean distance is giving us is an estimate of the distance between A and B. And it may be nowhere near close to the actual value. So let's go back to playing the 8 puzzle game that we have been working on from the previous lecture and look at problem solving as state space search. On your left is the start node of an 8 puzzle tile configuration, and on the right is the goal node. We want to search through the problem space for reaching from the start to the goal node. We have seen this in the previous lecture where we had looked at exploring all the nodes as it is expanded. Here we have the start node given to us, and the goal node is this configuration on your right. So what I wanted to show by repeating an exercise that I have done for uninformed search is that when I am using some form of problem domain information, which is roughly called a heuristic function, the whole idea of looking for a solution in the problem space has been directed. Rather than doing expansion at every level, like I expand everything here, like I have done for what we have named as breadth first search in our previous lecture, I have been very clearly able to go down a path which takes me to the solution in a directed manner. This is the motivation of using heuristic functions. The heuristic functions, the principal gain is often very spectacular. It is the reduction of the state space. The reduction of the state space is sometimes very, very surprising. Like if you talk of a very simple game that you must have played in school, like the tic-tac-toe, where you put circles and your opponent puts an X, and then you again put a circle and your opponent puts an X, and then you put a circle again to stop your opponent from winning, who then puts an X to stop you from winning. If you look at this small interesting game of tic-tac-toe, it has 9 factorial leaves. If we consider symmetries, the tree becomes 6 times smaller, but it's still quite large a number. But if you use a simple heuristic function, which we will be talking of during our informed search techniques, we get the tree down to just 40 states. So just looking at 40 states, I can decide who is going to win or who is going to lose in this game of tic-tac-toe. And that's what heuristics are so important for. Heuristics can help speed up exhaustive blind search, such as depth first and breadth first. In the previous slide, we were looking at something like a definitely breadth first search motivated by the heuristic function of misplaced tiles, and we could directly go into the solution by not exploring everything in the problem space.